In this lesson, we're learning about yet another specific instance of U substitution for integrals that involves trigonometry. So in this one, we're dealing with if you've got an integral that involves tangent and secant, and you have an odd power of tangent. It's a fairly specific strategy, but here it is. What you're going to do is you're going to reserve a secant and a tangent. And just like we did in the previous ones, you're going to take those things you reserved and sort of keep them next to the dx. Then you'll convert the remaining tangent powers, which are going to be even, of course, into secant using this identity. And then finally, at the end of the thing, you use the substitution u equals secant x, and the reason that makes sense is that your du will be secant x tangent x, which is precisely what we reserved at the beginning of the problem. So anytime you have an odd power of tangent, this is what you're going to do. Reserve a secant and a tangent, change the rest of the tangents into secants, and do a substitution. I've got a couple examples of that, so we'll take a look at them now. So here's this first example. Find the general solution to this differential equation. Again, I'm really just asking you to do an antiderivative, but solving a differential equation is just another way of asking that question. So our first step is sort of moving this dx over. So we end up with dy equals tangent to the fifth x secant cubed x dx. Then when we integrate, the left-hand side just turns into y, and the right-hand side is where we suddenly have work to do. Right? So the strategy that was listed in the problem was we're supposed to take this problem and reserve a tangent x secant x dx on the side. Now in order to do that, it means that I only have 4 powers of tangent x left, and I'll only have 2 powers of secant left. Right? Then I'm supposed to take all of my tangents that are left and change them into secants. Right? And we remember that tangent squared is equal to secant squared x minus 1. So here we'll end up with y equals the integral of secant squared x minus 1 times secant squared x minus 1 times secant squared x times this reserved tangent x secant x. Okay, so again, I'm just trying to follow the strategy we had previously. Now that this is set up, right, this is where we're supposed to notice, everything here has secant in it, and everything over here is the derivative of secant, which means I am perfectly set up for a u equals secant x substitution. Du will be, tangent x secant x dx. So when I go back through and substitute this stuff in, I'll have y equals the integral of u squared minus 1 times u squared minus 1 times u squared du. Right? And just like we've seen in these previous problems, by doing this little setup, we end up with a problem that's really, really quite simple to actually take the antiderivative of. Before I do the antiderivative, we have to simplify. So this is going to end up being u to the 6th minus 2u to the 4th plus u squared. So when I actually integrate, we'll end up with 1/7 u to the 7th. I'm going to substitute back in right now. So secant to the 7th x minus 2/5 secant to the 5th x plus 1/3 secant cubed x plus c. And we could do some factoring stuff with this if we wanted to, but this is our answer. I've ended all of these examples and videos and problems with, hey look, here's an answer that really doesn't look very pretty or very nice, but it can be done, and we're excited about the fact that we can get through these problems. So I have one more example, and this one is sneaky. This one's difficult. The reason it's difficult is that we have an odd power of tangent, and so we want to use this strategy of, reserve or pull out a tangent and a secant. Right? But, you might want to pause the video and think for a second, why will it be troublesome to reserve a tangent x and a secant x? The reason it's troublesome is that there isn't a secant x to be reserved. Like in the previous problem, there was that secant cube. There were 3 secants laying around, and I could just pull one of them out. In this one, there isn't a secant, so I may have to do a little bit of dark magic here. In order to do this, I'm going to sort of look at this and go, well, I know that I want to reserve a tangent x and a secant x. Like, I know I want to have those things set aside. how am I going to reserve the tangent? I'm going to reserve the tangent by just removing one of these, right? So I'm only going to have tangent squared x here. Now, how am I going to remove a secant x? There isn't a whole secant x to remove here, but what you could do is you could sort of counterbalance this secant x by putting a 1 over secant x into the problem. If you think about it, what I kind of did here when I put this tangent here is I put a 1 over tangent right here, and that just canceled out with the tangent cubed, right? I'm just going to have to look at how these two things interact with one another. When I do this, I'm going to see, oh, I have tangent squared x. Then here, where I have the square root of secant x over secant x, that's just going to end up being 1 over the square root of secant x, like when it's all, said and done. And I'll still have my tangent x secant x dx over here, right? We're almost ready to do the substitution. The one thing I need to do is I need to change this out for secant. So when I do that, I'll end up with secant squared x minus 1 over the square root of secant x times tangent x secant x dx. And now again, I'm in this position of this is ready to be the du. This has only secant terms in it, so we'll choose our u to be secant x. Our du will be our tangent x secant x dx. This should be a problem that you guys, if you haven't already done so, that you can finish on your own. So pause the video, do the substitution, and work through the actual arithmetic, and make sure you get it. So I'm seeing this as the integral of u squared minus 1 over the square root of u du. To do this integral, I'm going to do the sort of splitting up trick. This will become the integral of u to the 3 halves minus u to the negative 1 half du. So that'll be 2/5 u to the 5 halves minus 2u to the 1 half plus c. And then I just take we did a secant substitution, so I'm just going to take this and substitute it back in. Gives me 2/5 the secant to the 5 halves power of x minus 2 secant 1 half power of x plus c. And I've talked before about, I really like doing things like this, pulling out the 2 square root of secant x. It's worth your time. Pause the video and think about, if you did pull that out, what would it make the rest of the problem look like? You should have 1/5 secant squared x minus 1 plus c. If you're not seeing where that comes from, if you're having trouble with those algebraic manipulations, ask about it during class. That's definitely something that we can sit down and look at and practice while we've got some of that class time. So I'll see you there.